Hello and welcome to the third video in SCM's video tutorial series. I'm Nick Austin, and today I'll be talking about our capabilities in predicting mixture thermodynamic properties of polymer-containing solutions. So this is of course using our COSMO-RS module, but it also works just the same with COSMO-SAC. So before we jump into some calculations, I would first like to draw your attention to a few pages that we have on our website that will go into a lot more detail about this general approach than I will in this video today. The first of these pages describes the general theory as well as some extensions that are necessary for COSMO-RS in order to make polymer calculations tenable. That's this page here. Also in our tutorials section, we describe how to calculate a number of properties going through each step by step. So this is along the same lines of what I'll discuss today in this video. This is useful for calculating a number of important properties, so it's definitely worth taking a look to get started with using the GUI and doing polymer calculations. Finally, I will also just make a note that we have a polymer database. Now this is very analogous to our small compound database, which many users may be familiar with. This essentially just contains a lot of very common polymers, so you don't have to go to the trouble or expense of calculating these sigma profiles and coskf files on your own. So many common polymers are in this database. So as it says here, there are more than 200. Now I also of course don't expect anyone to memorize these URLs, so I will put links to all these pages in the description of the video. So before we do calculations, I would like to just briefly provide some background about the general theory of polymers with COSMO-RS, as well as a few extensions and important points that that might be good to keep in mind as you do these calculations. So the first of these involves how to actually generate these sigma profiles that are necessary for COSMO-RS calculations. So many COSMO-RS users are no doubt aware that the usual workflow for generating a sigma profile starts with a geometry optimization using DFT, for example, and then a subsequent COSMO calculation where you generate these surface charges, which eventually become the sigma profile. Now this approach is reasonably efficient for small molecules, but it doesn't necessarily have an obvious extension to large molecules like polymers, and indeed doing a DFT calculation on such molecules would be prohibitively expensive, as these molecules are simply by nature just typically extremely large structures. So we can't afford to do a DFT calculation on all of these structures. The approximation that we make to make this kind of calculation tenable is captured in this picture here. I think it speaks for itself, but I will just give you an idea of what's going on here. So rather than model an entire polymeric structure, so in the case of polyether-ether ketone, rather than modeling 100 or 500 or 10,000 repeat unit polymer, what we do instead is just model the trimer. We do a geometry optimization of the trimer, and then we construct the sigma profile only considering the surface points that correspond to the central monomer. So what this means is essentially, from the monomer's perspective, it sees what it would see as though it were part of a much bigger polymer. So on both sides it sees sort of a copy of itself, which is exactly the situation it would be in if it were in a much larger polymer. So this of course is an approximation, but our studies and comparisons to experimental values of activity coefficients seem to suggest that this approximation doesn't really introduce too much error. In fact, the errors that we observe with using this approach track very well with the errors we observe using COSMO-RS just for small molecule calculations. So we think this is a very reasonable approximation for polymers in COSMO-RS, and the way that you construct the sigma profile of an entire polymer is simply a function of this sigma profile that's generated from these surface charges of this central monomer unit, that's essentially just scaled according to the molecular weight of the polymer you're interested in. So if it were a 100 repeat unit polymer, you would essentially just take the sigma profile that's generated from these points and scale that by 100. So these large molecules in COSMO-RS introduce one additional complication, and what they do is they essentially invalidate one of the main assumptions in the traditional COSMO-RS combinatorial term. So that assumption is that the molecules in your solution have essentially comparable volumes and surface areas, and in the case of a polymer and a solvent, that's obviously a very, very bad assumption because polymers are much larger. So what we've added to the model in the case of polymers is a combinatorial term that comes from Elbro 1990, and it's a free volume based combinatorial term. And free volume is essentially an experimental molar volume minus a hardcore volume. So it's you can think of this as sort of empty space. And what this means for the user is that a bit more information is required. So specifically densities, which are then used to calculate molar volumes, are required. And it turns out that this model is rather sensitive to the values of molar volume or density, at least in many cases. So I would like to emphasize that it's very important to use accurate data, or as accurate data as is available to you here. So if you have experimental numbers for these molar volumes or densities, those are highly recommended to be used. If those aren't available, or if those are hard to come by for some other reasons, we do have some tools that help you estimate these values. But yeah, so there's plenty more information on this page. I refer you there if you have any other further or any questions about this approach in general. But let's get started with doing some calculations. So I'll just open the ADF input window here, and so for example, if you don't have, if there's a polymer you're interested in that's not in the database, you can do a calculation with ADF input to put it in the database, or to put it in your local database. I'll just do a simple calculation with polyethylene glycol. This molecule, of course, is in the database, but I'd just like to show you the general workflow here. So I'll draw the monomeric unit of polyethylene glycol. I will add hydrogens by hitting Control E. I'm also just going to shift a few things around here, so so it ends up in the geometry we desire. So we would like this to be just sort of a straight chain polymer, and this ought to do it. So the way we do this is we select both sites. You can hit Shift, at least on Linux, and click, and so select the two hydrogens that are attached to the sites along which you want to polymerize this molecule. Once you've selected those two, you go to Atoms, change atom type, and here the periodic table will come up, and you'll want to select this XX. This is our dummy atom type. This essentially just marks atoms as non-chemical atoms that are useful for some kind of labeling reason. So we've done that. This is essentially all the information we have to give the program, because this oxygen will polymerize by attaching to another carbon, which is attached to a carbon which is attached to an oxygen, and this carbon will also be attached to an oxygen. So this just sort of tells you where the polymerization occurs. Next, we'll go to Model Solvation. You see here COSKF Trimer. Just click the Generate button, and this will set up everything you need for a calculation, except for the preset. So you'll notice a few things here. First, it generates a trimer. It caps the N groups with methyl, or it makes methyl N groups rather. These are generally don't have too strong of an effect on the electronics, and they've been found to work quite well in our case. It also assigns something called COSKF atoms. So these are the atoms that correspond to this central monomer, essentially these atoms here that I've highlighted. So it marks those as special, and those are the ones that will be used to generate the sigma profiles. So as a final step, just make sure you set the COSMO-RS compound preset, and then you can run this calculation. So I have already run this calculation, and to save everyone the trouble of waiting for it, let's just open it up. So here's the COSMO-RS window. So what we do here is just go to add compound, and I'm just going to add these three polymer compounds. So these are the ones that we'll use for this video. So PEG is the one we calculated, and these two are two compounds from the polymer database. So we'll just hit open, and you see they're right there and available for us to use now. So let's have a look at PEG just quickly. So this is, I'll show you the results of the calculation. This is the optimized geometry. If you go here to COSMO surface charge density and then add the surface points, you see essentially the picture that we hoped for. So you see only the central monomer contributing to the sigma profile. So only these point charges are the ones that are used to calculate the profile. And the other monomers that are sort of the end monomers or the cap monomers are not used at all. So this is the picture we wanted to see, and this is, as I described, part of the general theory of using polymers with COSMO-RS. So let's close that. In order to use these polymers, there are a few things you should know. Most of this information can be accessed with compounds list of added compounds. So on this page, if we look at PEG, for example, we have to first mark it as a polymer. Those compounds that come from the database are already marked as polymers, but if you do a calculation, you need to tell COSMO-RS that it's a polymer. Also, a very important attribute of polymers is the average molecular weight. If you just leave this set to 0, I think it defaults to something like 10,000. So let's just go ahead and set it as 10,000. So as I mentioned, density is also very important for these calculations, and it's actually required to calculate the molar volumes, and therefore to calculate the combinatorial term correctly. So let's do a quick calculation with the PEG that we just calculated. In this case, we'll do a calculation that's at 353 Kelvin. So the experimental density I have for 353 Kelvin is 1.09. We'll look at this with benzene. So we'll open benzene from the database, and I believe the estimate will be a bit high here because it's at a, this should be at 298 K, so the experimental value I want to use for this is 0.814 in, yeah, so that should be the appropriate value for this temperature. Now let's take a look at activity coefficients. So let's look at two components here. So we'll use our PEG and we'll use benzene. I have some experimental data for this system, so I will put in the first of those points here. I think it is, actually I should also mention that many times it's much more common to think of these systems in terms of mass fraction, so that option works well, and that's, as I said, that's usually, polymer systems are usually given in the context of mass fraction. So the first data point I have here is at 0.026 weight fraction of benzene, which means that we will do a 974 here. And as I mentioned, this temperature is 353 Kelvin. So putting in all that information, we get essentially what looks like the output of a normal COSMO-RS calculation, with the exception of there being a few new numbers that have been added. So I'd like to talk about a few of those. Normally what we do is we report a mole fraction activity coefficient. That's quite common in the context of small molecule solutions. But in the polymer literature, what is more commonly reported are mass fraction-based activity coefficients or volume fraction-based activity coefficients. So those are also calculated whenever a polymer is present in the system. You'll notice we are also calculating a Flory-Huggins parameter. This is calculated directly from the free energy of mixing. So, so you can do this, and as I mentioned, I have a system that I compared to the experimental values of, so I will show you the results of that quickly. So this is by weight fraction benzene. Here's our first data point here. And this is the activity on the y-axis versus the weight fraction of benzene on the x-axis. And the experimental points are given in blue, and our estimated points are represented by this orange line here. So you see there's extremely good agreement with experimental values for this system. So let's take a look at another system then, or let's actually look at a different problem type. Let's think about some Flory-Huggins parameters. So we'll go back to this list of added compounds menu in order to change a few of the densities. So this next data point I have is at 100 degrees C, and it involves PEG. So we're going to change this to 1.07, and we have benzene also. This becomes 0.788. There are, by the way, a lot of good resources to calculate densities at different temperatures. For example, the Dortmund databank site is quite good, and that's what I used for a few of these solvent molecules. So we could go back to activity coefficient, but let's actually look at a binary mixture just to show you that you can use all these modules essentially in the exact same way that you would with small molecules. So the system that we're looking at now is PEG and benzene again. But as I mentioned, this is at 100 degrees C. And yeah, we'll do mass fractions again. So if we hit run, we get normal output. But now you'll see you can plot more polymer related attributes here. So you can plot, for example, mass fraction, which is also available for small molecules. But on the y-axis, you can plot, for example, the Flory-Huggins parameter, as well as weight and volume fraction-based activity coefficients. So let's take a look at the Flory-Huggins parameter. For this system, I think the experimental value I have is 0.13, and yeah, you can see that agrees quite well with what we're predicting here. Let's take a look at another system. I found some experimental data for polyvinyl acetate, and by the way, I should also mention that the polymers in the database do come preloaded with a density, or at least many of them do, those densities that I could find experimentally. These correspond to a liquid density or an amorphous phase density at 298 K. So this value I have is at 40 degrees, and so this is going to be a little bit smaller, 1.17. And we'll also take a look at water. So this we'll look at a system where the Flory-Huggins value is now much higher. So that density at 40 C is about 0.99. Let's now go back to binary mixture and change this to our polyvinyl acetate and water system. And as I mentioned, this is at 40 degrees C. And you can see, so the experimental value I have for this system at infinite dilution is 2.5. So you see it agrees fairly well with the experimental value, or sorry, with the estimated value we have here. So that's another important property, of course. Yeah, is Flory-Huggins. You can calculate those. Those are calculated, I believe, with almost every problem type. Let's take a look at another kind of problem. Specifically partition coefficients between polyethylene and water. So I found some data for this at 298 Kelvin. So let's look at polyethylene here. So we'll use low density polyethylene, which is about 0.92 density, and water again. but at 298, let's just say that's 1. And we'll add a couple compounds here for which I found experimental data. One is ethanol. That density should be 789. Phenanthrene. That density is 1.18. And finally Pyrene. That density is 1.27. So we can then go to partition coefficients, select user-defined 2 compounds, select our first phase as polyethylene, our second phase is water. Our temperature is 298, that's right. And we'll add a couple of these compounds that we're interested in calculating the partition coefficient of. So these are the 3 we've just considered. We can run these calculations and the results are shown here. I think all of these values are slightly high, and the reason for that is that you need to correct for a degree of crystallinity that exists in polyethylene. So polyethylene is not entirely amorphous. There's some fraction of polyethylene that exists as a crystal. So it's not really possible for these solutes to dissolve in them, and that in this case ends up resulting in a slightly overestimated log p-value. So more goes into the polyethylene phase than should, is what that means essentially. So that's something you have to keep an eye out for if your polymer has a certain fraction that's expected to crystallize. You do need to correct for that effect in many cases. So yeah, as a final example, let's look at gas solubility. It's also a really important property. We'll go back to the list of added compounds menu, and we will consider polyethylene. And I've found some data for 6 gases. There was actually quite a bit more data, but a lot of the gases were above their critical temperature at 298 K, and I thought that conflicted a bit with some of the COSMO-RS assumptions, so I thought I would leave those out. So I've included the gases that were still subcritical at 298 and 1 bar. So I'll just do one calculation here and show you the results of the others. So for carbon dioxide, we need to estimate the density of the hypothetical liquid phase, and that value is 0.9. That's the value I'm using. Also, because we're doing gas solubility, we need some idea of the vapor pressure. We can just use our built-in tool here to estimate the vapor pressure equation for that. So then we can go to solubility in a mixture or solubility in pure solvents. It doesn't matter. Select polyethylene as our solvent, and then here select carbon dioxide as a gas. All of this is correct, and what we get here is a value that typically corresponds to small molecule solvation properties, but these can very easily be converted to more traditional gas polymer solubility units. So typically gas polymer solubility units are given in some volume of the gas divided by a volume of the polymer times some pressure unit, and that's quite easy to convert from this. And so indeed I've done that for these 6 solvents, which by the way are carbon dioxide, ethane, propane, propene, sulfur hexafluoride, and alene. So looking at those results, we observe a very good correlation between our estimated solubility and our experimental solubility that I found in the literature. One thing you'll probably notice is that the slope of this line is 0.34. It's not so this is the line of best fit. This is not as close to 1 as we would like, but this effect is again explained by the effect of crystallinity in polyethylene. There's a large portion of polyethylene in which no gas molecules can dissolve, so that in this case represents an overestimation that COSMO-RS makes as compared to the experimental values. So that that covers quite a few calculation types. Everything essentially works the same way that it does with small molecules. So it's something that you can play around with. Of course, I will just very briefly mention 2 more things. In list of added compounds, you can also add compounds by smiles, and this is specifically for polymers. There's something called curly smiles. There's good examples on the polymerdatabase.com. So for example, this is a curly smiles. You can add this just as you would a normal smile string to generate a quick estimate if you don't want to do a full DFT calculation for these. And I'll also mention briefly for a ternary mixture, if, for example, we just looked at this system where the densities are probably no longer meaningful. If we look at this system, there's a few things. So, for example, Flory-Huggins parameters are typically defined in terms of a binary mixture, but in this case I've included a Flory-Huggins parameter that corresponds to a benzene and hypothetical co-solvent, or excuse me, a hypothetical copolymer of polyethylene and polyvinyl acetate in this case. So that's the Flory-Huggins parameter that corresponds to a copolymer, and specifically a block copolymer of polyethylene and polyvinyl acetate, which is just something you can use to explore the dependence of the Flory-Huggins parameter on copolymerization ratios. So yeah, that wraps up a basic tutorial of the capabilities of polymers with COSMO-RS. I will also just leave you with a few references from which I've drawn my experimental data. So as always, if you have any questions about this or any suggestions or recommendations for us, please feel free to email us at support@scm.com. Thank you for your attention, and I hope this can be useful in your research endeavors and can produce useful results. Thanks.